Welcome to the deep dive. Today, we're looking at a scenario that, well, it forces you to reconcile the extremely small with the catastrophically powerful.
It really does.
We're not talking about those huge stellar black holes, the ones that swallow light in entire star systems.
No, nothing like that.
Instead, we're focusing on a hypothetical threat so tiny it would be completely invisible, smaller than a single atom, yet it could possess the power to just burrow right through our planet.
It honestly sounds like pure science fiction, I know. But this is where real theoretical physics is right now, looking at these objects known as microscopic black holes, or MBHs.
And that's our deep dive today. We want to analyze the physics behind them, explore where they might come from, like high-energy particle collisions,
Right.
how they would interact with Earth, and the, frankly, chilling reason why our sources confirm that if one entered the Earth today, we have no way to stop it, or even see it coming.
The central paradox is really what makes it so fascinating. How can a particle, something vastly smaller than a single cell, wield the gravitational pull of something? Well, something unimaginably massive.
It's a total departure from the black holes we normally think about.
Completely. And as you said, the relevance for you, our listener, is immediate. Because if the models are right, the consensus is that we wouldn't know about it until after. Until after it's already left its mark.
Okay, let's unpack this gravitational nightmare. I think we need to start with the basics. What exactly is a microscopic black hole? I mean, how small is subatomic?
We're talking about the truly quantum scale, getting close to the Planck scale, which is kind of the fundamental boundary of physics as we know it.
So really, really small.
Think of a proton, already minuscule, right? An MBH would be thousands upon thousands of times smaller than that. It's a singularity compressed down to the absolute minimum possible size for its mass.
And its origin isn't some distant galaxy. It could be local, potentially right here.
That's right. The source material really focuses on two main ways they could form. The first is, statistically the most likely, these incredibly powerful cosmic rays hitting our upper atmosphere.
Just happening naturally.
All the time. When these rays, which have energies far beyond anything we can generate on Earth, hit an air molecule, the energy density from that collision could, theoretically, be enough to collapse space-time into a tiny black hole, just for an instant.
And the second one, the one that got everyone nervous when the Large Hadron Collider was being built.
Is that we might create them ourselves in a lab.
Right.
Exactly. Scientists working in high-energy physics, at the tera-electron-volt scale, they know that if certain theories about extra dimensions are correct.
Theories that say gravity is sort of leaking into other dimensions.
Yes. If that's true, then the energy needed to create a microscopic black hole drops a lot. It goes from being cosmically impossible to something we can maybe achieve in an experiment.
But the consensus is that one of those would just evaporate instantly.
Right. Almost instantly, yes. But the possibility, that's what drives the research. That's what we have to understand.
So let's say one does breach our atmosphere. It seems like its fate, and maybe our fate, depends entirely on how fast it's moving, the speed factor.
That is the single most important variable. If an MBH is moving at relativistic speeds, say 99% of the speed of light, it just punches right through the Earth.
In a fraction of a second.
Instantaneously. The time it spends interacting with any of the Earth's mass is so brief that it has no time to slow down. It just exits, maybe knocking a few atoms aside. Scenario A, blink, and you miss it. It's gone.
But what if it's slower? Maybe it was created nearby, almost stationary, or something slowed it down. Then it becomes what the sources call active.
And active is where things get serious. It means the gravitational interaction is long enough for it to start absorbing mass.
Okay, so it's actually pulling things in now.
Yes. And remember, its local gravitational field, the tidal forces right next to it, are immense. We're not talking about it sucking up matter like a vacuum cleaner. It's much more violent. The gravitational gradient is so sharp, it literally strips particles away from the atoms they're bound to.
So it's just consuming everything in its path. Air molecules, water, rock.
Rock, metal, anything. Whatever particles pass within its event horizon are just gone.
And there's no way to see this happening.
None. This consumption is pure gravity. There's no light, no X-rays, no electromagnetic signal at all because it bypasses all of that.
Yeah.
It is a pure silent engine of gravitational absorption.
That is a terrifying image. And it leads us to the path it takes through the planet, what the research calls the silent tunnel.
That term, the silent tunnel, it just perfectly captures it. If a big asteroid hit the Earth, you'd get fireballs, shockwaves, massive disturbances.
Total chaos.
An MBH just punches a tiny dark hole through the interior. It doesn't ignite anything. It doesn't cause a big explosion. It just displaces and absorbs matter as it goes. It moves like a dark bullet.
A dark bullet tunneling through the mantle. That's unsettling. But it brings up the next question, which feels like a really worrying feedback loop. If it's consuming particles, its mass has to be increasing, right?
It
Does
does.
this tiny black hole stay tiny?
And this is where it gets really interesting. If it slows down enough and starts to reside inside the dense parts of the Earth, say the core, it will absolutely accumulate mass.
And as its mass grows,
Its event horizon grows, which means it can sweep up more particles, which makes it grow even faster. It's an accelerating process.
so the longer it's inside the planet, the faster it eats.
Hmm.
This leads us right to the counteracting idea, the one thing that could stop it. The paradox of evaporation.
Right, and here we have to shift our thinking completely. We have to bring in quantum mechanics. For big stellar black holes, evaporation through Hawking radiation is, well, it's negligible. It takes trillions of years.
But not for these.
For MBHs, it's the dominant effect. Hawking radiation is this quantum process where the black hole basically leaks energy and mass back out into the universe. It shrinks.
And I've always heard that the smaller the black hole, the faster it evaporates. So is that the good news? It should just vanish in a flash of energy.
That is exactly what should happen. In a vacuum, the decay rate is inversely proportional to the square of its mass. So a tiny subatomic black hole should disappear in an almost instantaneous burst, way too fast to be a threat.
Okay. So where is the catastrophic danger point? How does the Earth itself become the problem?
The danger is at the tipping point. The point where the environment, the dense material of the Earth's core, provides mass for it to eat faster than it can radiate that energy away.
So it's a battle.
It's a cosmic battle on a quantum scale. You have rapid quantum decay trying to destroy the black hole, and you have the incredibly dense matter of the Earth's interior feeding it, trying to make it grow.
And if that balance shifts?
If the accretion rate, the rate it's eating, exceeds the Hawking radiation rate, the MBH stabilizes, then it starts to grow exponentially. And that is when it becomes a lingering, devastating threat to the planetary interior.
It just feels unbelievable that one single, slow-moving subatomic thing could cause what the sources call a local catastrophe. What does that even look like?
The energy transfer is just immense, even on a local scale. You're talking about so much energy being absorbed and released in a concentrated area that it could destabilize huge regions of the mantle or crust. And pretty quickly, too.
So if this dark bullet did tunnel through, or if it got stuck, what would we see? What are the scars we'd be looking for?
The effects would be entirely seismic and magnetic. You wouldn't detect the object itself, only the consequences of its passage.
Like its wake.
Exactly. The sources point to localized seismic activity, miniature earthquakes, but not caused by tectonic plate shifting. They'd be caused by the sudden removal, the displacement of mass deep underground. Imagine a chunk of the mantle just vanishing.
An earthquake caused by a void.
Mhm.
That puts the danger into context.
You'd also see bizarre distortions in the magnetic field. As it consumes charged particles in the core, it would create these highly turbulent magnetic anomalies. And finally, just immense heat, a scar of thermal energy left along its path.
Which brings us back to the most critical and honestly the most frustrating part of this whole thing. We can't detect it as it's happening.
It's a ghost confirmed only by the destruction it leaves behind. It's a profound limitation of our current physics. We rely on seeing things through electromagnetic signatures, light, radio waves, X-rays.
Or gravitational waves for the big one.
Exactly. But a quantum scale, purely gravitational absorber, it generates no measurable electromagnetic signature, and the gravitational waves it would produce would be far too small for us to register.
So we're stuck in a purely retrospective analysis. We see a weird heat spot, a mini earthquake, a magnetic blip, and we have to work backward and ask, was that just geology, or is that the trace of a passing MBH?
Precisely. And that's why this is studied so seriously, often in, closed academic circles. The very systems we rely on to monitor our planet are built for things we understand. And MBH operates completely outside that framework.
So what does this all mean for you, the listener? We've just analyzed a hypothetical threat that's invisible, it's silent, and it only confirms its existence through destructive side effects, the scars of the silent tunnel.
We've really highlighted that delicate balance, the insane contrast between its subatomic size and its immense gravity, and that fundamental tension between quantum evaporation, which should destroy it, and catastrophic mass secretion, which could make it grow inside a planet like ours.
And it forces us to grapple with the idea that the universe, or even our own experiments, might generate forces that are just completely below our technological radar.
It does, and this really raises an important and I think a provocative question for you to consider. If we accept that high-energy collisions, whether they're natural cosmic rays or man-made, are theoretically capable of creating a catastrophe that is physically undetectable in real time, what does that imply?
What does it imply about other things we see but don't understand?
Exactly. What about other unexplained physical phenomena that we currently blame on geology or climate? Could some inexplicable temporary magnetic distortion or a strange localized seismic spike already be the subtle trace of a fast-moving MBH that has already come and gone? We rely on theoretical physics to predict these unseen dangers. And this scenario shows just how far ahead of our detection abilities that knowledge has to be.
A truly sobering thought about the boundaries of what we can and can't see. Thank you for taking this deep dive into the silent tunnels of theoretical destruction.